अच्छी प्रॉपर्टी होगी, it may lose that property. So that's this. But in case of identity, it may not happen. For some time, it may happen identity by adjoining an identity that semigroup may lose certain properties, but we'll see that later on. But in case of zero, we cannot adjoin zero, so that it will carry all the properties. That's not true. Okay. So next, we define a null semigroup. Null semigroup. So let's take let S be a semigroup with zero. Let S be a semigroup with zero, and if x into y is equal to 0 for all x, y belongs to S. If the product of any two elements of S is equal to 0, then S is called a null semigroup. Then S is called a null semigroup. That is called a null semigroup. Okay, it's a null semigroup if the product of any two elements is equal to 0. So next we give the example of semigroup, which is very important. As in case of groups, the group of permutations is very important. Here the group of all functions, not only the permutations, but the group of all functions is very important. So let's define that semigroup. Let x be not equal to 5 be a non-empty set, and that Tx, it is the set of all functions from x to x. Then Tx is a semigroup. In fact, it's a monad. Then Tx is a monad where the binary operation is the composition of mapping. Where the binary operation is the composition of mappings. That is if f comma g belongs to Tx, we define fg from x to x by xfg is equal to xfg. So that's a composition. So clearly it's a map from x to x, because f is a map from x to x, g is a map from x to x. Their composition is also a map from x to x, which is defined by this: fg of x is equal to xfg. So actually I already mentioned in the lecture 1 that I would always write element on the right hand side of the map. So this is a semigroup, and this semigroup is called the transformation semigroup, or we can say full transformation semigroup. The semigroup Tx is called the full transformation semigroup. Full means we are taking all the mappings. Full transformation semigroup. And any sub semigroup of we don't have defined yet sub semigroup. So that's called transformation semigroup. It's a semigroup. It's a set consisting of all the mappings on a given set, and it forms a semigroup with respect to the composition of mappings, and such a semigroup is called the full transformation semigroup. Now we define left zero semigroup. All these semigroups are very important. Null semigroup, left zero. Now we define left and right zero. This Tx, it's very important in our study. So let's define left zero semigroup. Left zero semigroup. Left zero semigroup. So left zero semigroup is a semigroup whose every element is left zero. जिसका हर कोई element left zero होगा. ऐसे semigroup को हम कहेंगे left zero semigroup. a semigroup S is said to P is said to be a left zero semigroup. It's called a left zero semigroup if AB is equal to B for all A comma B belongs to S. So that means for all B in S, AB is equal to B. So B is left zero. And S is and it is said to be right zero. If it's every element is right zero, it's said to be right zero semigroup. It is said to be right zero semigroup if AB is equal to A. Sorry, this is here B. Sorry, it's A here. A is on the left side. A is the zero. Sorry, A is the zero. Here B is the zero. AB is equal to B for all A B belongs to S. So a semigroup is left zero if it's each element is left zero. For all A in S, AB is equal to A. For all A B in S. So that means this A is left zero. So it is true for each A. Every element is left zero. And here AB is equal to B. That means B is right zero. So that means every element is right zeros. So that's the definition of left zero semigroup and right zero semigroup. So now we have one more example of a semigroup with zero. Let's take this semigroup. It's a closed interval 0, 1, and now define the operation. So let's define this operation. Define x into y is equal to minimum of x comma y. Then U is a semigroup with 0, 0 and identity 1. So again, if we define like this, if we define x into y is equal to maximum of x comma y, then 1 is the zero of the semigroup. Can easily verify this. 1 is the zero of this semigroup. So then because then x into 1 is equal to, it's the maximum of x and 1, while x lies in this interval 0 to 1, so it's equal to 1, and which is same as 1 into x. And you can verify that 0 is identity in that case. 0 is not the zero element. So because in that case 0 into x, what x lies in this interval, so what's the maximum? Maximum is always x. It's equal to x, which is equal to x into 0. So then so therefore in this case U is a semigroup. U is a semigroup with 0, 1 and identity 0. So now we define product of the subsets of a semigroup. So now we define the product of subsets of a semigroup. So let S be a semigroup, S be a semigroup and A comma B be subsets of S. Suppose there are any subsets of S. Then we define AB. It's just the product AB such that A is in A, B is in B. B is in B. So suppose if you want to define A into A here, A into A, which we denote by A square, it's equal to A1 into A2 such that A1 belongs to A and A2 belongs to A. And it's not equal to A square. It's not equal to A square. This is understood. It's not equal to A square. It's the product of any two elements of A square. It's not the A square where A belongs to A. So in case this B is singleton set, then what's the product of A with B? Where B is a singleton set. Suppose B is equal to, say, singleton set B. If B is equal to singleton set B, then we write AB, which is equal to A into singleton B, and this we write as AB, just AB. So AB means the product of the two subsets of a semigroup S. One is A, second is the singleton set B. It's equal to, say, AB here on the A values, because B, it's the singleton set, B is fixed. A is equal to B. A is equal to B. Now we have some notations. If S is a semigroup without identity, if S is a semigroup without identity, one, then we write this SA. So what's SA? S is a subset of S, singleton A is a subset of S. So SA is in S. So it's the product of two subsets of S. One is S itself, second is the singleton set A. So it's equal to SA, so that S belongs to S. So S belongs to S. Then it may not contain A because it's without identity. In case S contains an identity 1, then it will definitely contain A, because by putting S is equal to 1, then 1 into A is equal to 1. So in that case, so A is inside of this set SA. But it may not contain A. ये A को कंटेन नहीं कर सकता इन जनरल, क्योंकि S में आइडेंटिटी नहीं है. अगर S में आइडेंटिटी होती, हम S का वैल्यू वही आइडेंटिटी ही लेते. यहाँ पर पर्टिकुलर केस में पर्टिकुलर चॉइस हम लेते S की, S इज इक्वल टू 1. तो उस केस में क्या हो जाता, 1 इंटू A, ये A के बराबर आ जाता. तो A इस सबसेट का एलिमेंट बन जाता, मतलब A इसका एलिमेंट A उस केस में इस सेट में आ जाता. मगर अब चूंकि S में आइडेंटिटी नहीं है, तो ये A को कंटेन नहीं कर सकता इन जनरल. कुछ केस में कर भी सकता है, S में कोई एलिमेंट ऐसा आ सकता है, so that this product will become the identity, but in general it may not contain, so that this product will become A, but in general it may not contain A. It may not contain A. So now we have this, then we take these sets S1A. What's S1A? So it will be equal to, क्योंकि अब S1A में A भी होगा और S के एलिमेंट्स तो हो गए ही, it's equal to SA union A. SA union A. And you can see this A S1 is equal to A union AS. A union AS. इसी तरह से अगर आप S1A S1 निकालोगे, S1, now we'll take S1A S1. S1A S1. What's S1A S1? S1A S1. It will be equal to it's SA union AS. If you take element 1 in S1, it will be AS. Now if you take one element from both the semigroups S1 and S2, it will be A of just A. It's A here. So it's a union of these. Not only these three. There's one more set union SAS. So it's SA union AS union singleton A union SAS. So you can easily verify this. Suppose you take any element in this union. So if it is here, then obviously it belongs to this. Suppose you take S element. Let's denote this union by T. Let me denote this by T. मैं इस यूनियन को T से डिनोट करूंगा. So let's take X in T. If we take X is in T, then X is either in SA or in AS or in A or is equal to A or in SAS. मैं एक केसेस दूंगा अलग अलग. तो सपोज फर्स्ट केस में ये लूंगा कि X, suppose X belongs to SA, then X is equal to SA, where S belongs to S. So this is same as SA1, where S belongs to S में S तो S में है ही, so ये S1 में भी होगा and 1 belongs to S1. So what's this S X now? It's SA1 where S is in S1, 1 is in S1. तो last के जो दो elements हैं ना ये दोनों S1 में है. So it means that it belongs to S1A S1. So in case X belongs to SA, then it is in this set. Now I take second case. Suppose X is in AS. That's similar. So now suppose I take this third case. X belongs to singleton A. So this is the similar case as this one. Now if X belongs to A, it means that X is equal to A, and that can be written as 1A1 because 1 is identity. 1 belongs to SK. So it's a product of three elements. First and last element, they belong to S1. So that means it belongs to S1A S1 again. Now the last case, if it is in SAS, if X belongs to SAS, it means that X is equal to S1A S2, while S1 comma S2 they belong to S. So that means X is equal to S1A S2. Since S1 and S2 they belong to S, therefore they also belong to S1 because S1 is bigger than S. So while these S1 comma S2 they belong to S1. So again this X, it is the product of three elements, and last two elements, first and the last element, they belong to S1. So this implies X belongs to S1A S1. So in all the cases X belongs to S1A S1. So that means that union is subset of so that is SA union AS union SAS union singleton A. It is subset of S1A S1. And converse is true. If you take any element here, you take the different choices of elements of S. So then you can easily verify that this S1A S1 it is subset of this union. So that's this union is equal to S1A S. So thank you. This is the this was the last topic of this lecture. So in the next lecture we will derive certain properties of semigroups. So as you know that the groups have very important property by Cayley's theorem. Every group is isomorphic to permutation group. Every group is isomorphic to permutation group. And here we prove the analog of the Kelly's theorem in semigroups. We prove that every semigroup is isomorphic to some transformation semigroup. So that we'll discuss in next lecture. Thank you.